So let's get started again. So in the last class we were looking into one of the SGS models. We started with one subgrid scale model, which is Smagorinsky model, right? So Smagorinsky. So in Smagorinsky model, we essentially used idea similar to Businesque, where instead of an eddy viscosity, an SGS viscosity is used, and this SGS viscosity or new SGS is essentially a function of the filter size. That means mesh size if you use implicit filtering. So your numerical length scale is directly going into the simulation, right? The eddy viscosity, the SGS viscosity is directly depending on mesh size. Okay. Um, and then there was a model constant CS, which was user dependent. That was one of the disadvantage. So in SGS or in a Smagorinsky model, we had essentially two unknowns coming out. One is new SGS, other one was KSGS. This KSGS is introduced only, let's say, if you want to solve one equation for KSGS. Uh, so before that, I would like to talk about this new SGS. So if you recall new SGS in the Smagorinsky, this was CS delta square, that is your length, some idea like a mixing length, right? L square, followed by an inverse time scale, which is square root of 2 Sij. This is filtered strain rates. This is your time scale, inverse time scale. Okay, with that you are getting meter square per second, consistent with the dimensions. So here the one problem you would face here is that close to the wall you will have large strain rates. This is discussed in eddy viscosity framework. Very close to the wall, the strain rates. This is resolved strain rates here, right? Sij over bar implies resolved strain rate. That means something you are computing for, and this goes large close to the wall. But new SGS should account for only SGS fluctuations, not for all the turbulent fluctuations. Therefore, some kind of damping is required or wall correction is required, right? So you can take a note here, what is called near wall effects. So new SGS, okay, near the wall, let's say, this becomes very large due to this becomes very large due to large value of the resolved strain rate, that is S over bar. Okay, so this is nothing but your 2 Sij over bar, Sij over bar, large strain rate. So one option to solve this is using a damping function. Okay, so this becomes unphysical here. New SGS, this large value, okay, this is unphysical because SGS fluctuation should go to 0. Should go to 0. So you would need a damping function here, right? One option is option 1. You can use a damping function similar to an idea that we used in eddy viscosity framework. A damping function like f mu equal to 1 minus e raised to minus y plus by 26, where y plus is is your near wall distance. Y plus is near wall distance. Another option is to have a limiter, the limiter on the length scale, right? So the delta, so we can put a limiter on it so that new SGS reduces. For example, if you look at let's say near wall mesh, let's say is like this. If I take a mesh close to the wall, but in the other directions, this could be like, this is the delta y, but the delta x, let's say, is like this. Okay, a large delta x and a small delta y, and maybe a large delta z also. Let's say if I am taking in the other direction, a large delta z. So together it will make the delta v, or the delta itself is a cube root of delta x, delta y, delta z, right? So this can be larger. So this can be reset using a limiter, using the same idea as this mixing length, using von Karman constant and the near wall distance. So in option 2 we use a limiter. What we do for this limiter is, the delta is set as minimum of the delta v I j k, that volume at any location I comma j comma k index, or you take the mixing length. Kappa is the von Karman constant, y is the near wall distance as before. Okay, where kappa is 0.41 von Karman constant and y is near wall distance. So obviously in this situation here, the y will be much smaller. So for example, if delta v becomes large because you have used a cell, a stretch cell, usually this happens, like you in the wall normal direction you would make delta y smaller to capture gradients there, but the horizontal grids, that is in the x and z directions, you sometimes have bit longer distance, but delta v will then take that effect from the other two directions, right? So resetting that to kappa y will solve this issue. So this limiter can help with the near wall correction terms, okay, for the new SGS. So now the other question is about, if you are having KSGS in the computation in the Smagorinsky, then how to get this KSGS? One way out is to solve for a transport equation, which is a popular technique in some of the open source codes as well as commercial solvers. They use a transport equation for SGS kinetic energy. Okay, so we'll see what it does. So we'll have one equation KSGS model, that is together with the Smagorinsky, we can use this to get the KSGS in the formula. Okay, so here the transport equation goes similar to your K modeled equation. So we have dou K SGS by dou T plus dou by dou xj of your filtered velocity and the subgrid scale kinetic energy that you are computing for, equal to the diffusion term dou by dou xj of nu plus nu SGS dou K SGS by dou xj, and then a production rate. This production rate is for SGS fluctuations, PK SGS, and the dissipation rate. But the dissipation rate is not for the SGS, because remember the idea of an SGS model itself is to dissipate all the energy that is in the system. Okay, So that will be the true rate of dissipation rate. Okay, but these are unknowns. I am computing for KSGS, which is an unknown, but in that equation now I need to figure it out what is PKSGS, how to get epsilon, right, and also whether nu SGS has to be same as nu SGS in the Smagorinsky or not. So in the equation what we do is nu SGS is calculated slightly differently here. Okay, uj you don't have to worry because resolved velocities are available here. So this uj, this is the filtered or resolved, right, resolved velocity. This is known, you don't have to worry about it. But the unknown part, the first one is of course nu SGS. This is slightly computed differently than in the Smagorinsky here, in the one when you use one equation model. So what we do is there's a model constant Ck and then delta, the length scale. So that makes it meter here. So you still need a velocity scale, right? So the velocity scale can come easily from KSGS itself because you are computing for the KSGS. So you can use square root of KSGS. So that makes this meters per second, meter square per second. So here of course the Ck value, again Ck value changes from 0.05 to 0.1 in different codes while implementing or flow dependent, and delta is same as before, it is the filter size. But the other two things you need to figure it out, one is PKSGS, other one is epsilon. So now what should be the production rate of KSGS? If you look into an energy spectrum, let's say I have an energy spectrum E of K, K is the wave number here. Okay, so this is the wave number spectrum, let's call this K is the wave number. So we already seen this kind of a graph. Okay, so in this plot, let's say somewhere here is the inertial subrange, right? So if this is the cutoff size here and this is the absolute dissipation rate is, let's say epsilon is here, up to here is where you are resolving all the scales up to here, and the last part is modeled. So what will be the dissipation rate up to the resolution? What should that be called? Isn't that the SGS dissipation rate? This is nothing but epsilon SGS. Okay, this is what is being resolved in your LES, right? So the last part is modeled here, this one. So if epsilon SGS is the at the cutoff, this is the epsilon SGS, and we learned from Kolmogorov hypothesis that there is a dynamic equilibrium here. Shouldn't that be the PK SGS? Whatever is being drained out of the resolved data should be the production rate of the SGS, right? So this essentially becomes your PK SGS. Okay, so PK SGS is set equal to epsilon SGS, and epsilon SGS can come easily from the resolved data, as I said. So that means I can use 2 nu SGS and the resolved strain rates Sij bar. This is not same as epsilon because epsilon was your you had nu as well as Sij prime over bar implying ensemble averaging. Here this is filtered strain rates here, okay, right. So Sij is the filtered strain rate. Sij bar is, you can say, resolved strain rates. Nu SGS is known, so Pk SGS is set equal to epsilon SGS here. And finally, epsilon itself has to be given, the last sync term in the this one equation KSGS model. So that comes from, so finally the epsilon here is given empirically. So we take C epsilon, a model constant, and then KSGS you have access to, you are computing for it. So 3/2 of KSGS divided by, of course, whole thing divided by delta, which is your length scale, right. So this essentially gives you, this is nothing but your meter cube by second cube divided by meter, which gives you meter square by second cube, dimensionally correct. So this empirical formula is used to get epsilon here, okay. And of course C epsilon is 1 here. Here C epsilon is 1. So this will complete the Smagorinsky model itself with the combination of one equation KSGS model, okay. So now despite this, we still have new SGS computed where the model constant is varying. You have to choose either this constant or, so there is a user dependent part in choosing the model constant here, right. So one way of getting rid of that is actually go to another type of SGS model, which is called dynamic subgrid scale model, so, or a dynamic Smagorinsky model, where dynamically the constant is computed. Now the constant is fixed for a given case by user, so it is static. Dynamic implies on the fly, that means when you are running the computation, you are going to compute that constant at each time step, at each iteration you are going to compute this, okay. Any doubts on this before we move to a dynamic Smagorinsky model? No, okay.